Everyone. Welcome to Computer and Network Security. In today's lecture, we are going to see how some of our cryptography concepts are applied to real-world scenarios, to real-world protocols, and the internet at large. In particular, we want to discuss three main systems. We want to discuss SSL and TLS and how they actually apply to web browsing. We want to discuss IP security and how it solves many of the security problems that we already have on the internet. As an application, we're also going to look at the end-to-end encryption system of WhatsApp. And if we have time, we're also going to take a look at Tor and see how an overview of how it operates. We'll start with internet security. In particular, we want to look at the security features at different levels. We saw how some security features can actually be implemented at the application layer level. Now we want to see how it can actually be implemented at the transport layer level, mainly through the protocols that are known as SSL, or the secure sockets layer, and its successor, the TLS, or transport layer security. Okay. So basically, transport secure sockets layer that was proposed by the company Netscape actually, and then it was standardized in the TLS protocol, or transport layer security, as a reliable end-to-end secure service. It extends TCP. So it's a layer that sits between the application layer and TCP to provide actually security services to web browsing. Okay, so SSL and TLS depend on having a TCP connection at the transport layer first. Okay, so it relies that TCP already provides a reliable end-to-end service and provides security features on top of that. Okay, SSL, we're going to discuss first SSL, and TLS is actually very similar to it, except for some differences in how the protocols are applied. SSL is actually not a single protocol. It has two layers. One layer is where we find the SSL record protocol, and this is where all the security features are implemented. If you have authentication, if you have confidentiality, everything is actually implemented in the record protocol. On top of that, you have another layer where you find three protocols that are necessary for exchanging information between the two ends of the TCP connection. You have the handshake protocol, which provides additional handshaking messages on top of TCP or after TCP is established. You have the alert protocol that serves as a protocol to send warning messages between the endpoints of the TCP connection. And you have something called the change cipher spec protocol, which is a very simple protocol that is just there to change the status of the connection from in negotiation to something that is set up and ready to operate. We have to be clear about two main concepts that are in SSL. These are the concepts of a session and a connection. The session is basically a security association between the client and the server, and it is something that is established after the TCP connection. This is where the client and the server will exchange actually security parameters, will agree on the protocols that they will use, because SSL and TLS, they actually support a wide range of security protocols and features and options that should be negotiated between client and server. Once a security association is available, that means actually that the client and the server can start exchanging secure messages between them. How do they exchange secure messages? Through what is called a connection. And the connection is a transport within the session. It is not the TCP connection. A connection is actually a concept in the SSL layer. Basically, every connection is associated with one session. So typically, the client and the server will have one session between them. You can actually negotiate more than one session, but this is typically not done. They will have one security association or one session between them, and they can have several connections, and typically each connection can be associated with one TCP connection. So that if you have a client communicating with the same server and there is more than one TCP connection open between them, there can be only one session but several transports or several connections between the client and the server in this case. Okay. What kind of security services are offered by SSL? Mainly message integrity and confidentiality. Message integrity is done using a message authentication code, or MAC. The MAC is based on a symmetric key that is exchanged between the client and the server. In SSL, the MAC is generated using a protocol that is similar to HMAC, and in TLS, HMAC is actually used. Confidentiality, on the other hand, is based on symmetric encryption. Many things are actually supported, such as AES, IDEA. There are several stream ciphers that are supported, like RC4. Different versions of TLS support actually different cryptography suites. For example, the newest one is TLS 1.3. In stream ciphers, it only supports RC4 and something called ChaCha, which is also a stream cipher. Many of these, the ones that you see here, are no longer supported by TLS because they have been deprecated. They are old and insecure, and so they're no longer supported. But over the years, there has actually been several versions of symmetric encryption systems that have been supported by SSL and TLS. How does it work? We'll start actually with the main protocol in TLS and SSL, which is the record protocol. The record protocol receives the payload from the upper layer and is responsible for fragmenting it. So it receives the payload as a stream of bits and is responsible for dividing it into fragments. After fragmentation, there is an optional stage of compression, and it is optional. You can actually just pass the fragment as it is to the step after that. The reason for having compression is that you are going to actually add additional bits to the message for the sake of verifying integrity. You are going to add a hash to the message. This is how we actually verify the integrity of a message. We send the message concatenated with its hash, and if we encrypt both, then we have confidentiality and integrity. So since you are going to add a hash of the message, that means that the size of the final message that you are going to send is larger than the payload that was generated by the application layer. And so compression, the goal of compression is that after you compress the fragment and you add the MAC, you will end up with a message that has the same size, or more or less the same size, as the original fragment that was generated by the application layer. That's basically the size. Compression, as the compression mechanisms that are supported by SSL and TLS are lossless compression. So it is necessary that the entire data is retrieved as it is at the other side. And so the MAC is generated by a protocol in SSL that is very similar to HMAC, and in TLS by the actual HMAC protocol. And we know that in HMAC, there is no encryption to the hash. Basically, you feed to the hash a secret key, which is called the write MAC secret. And the secret key that is used by the client can actually, or is different from the one that is used by the server. There is a secret key for the hash, or for the generating the message authentication code, and there is another secret key that will be used for encryption. And as you see here, encryption applies to the compressed message plus the MAC. So you encrypt the message concatenated with the MAC, okay, and then you have the encrypted fragment in this case. Okay, and the key that is used to encrypt is different from the key that is used to generate the MAC, and those two keys at the client are different from the keys that are used at the server. So there is a key exchange that is going to be used by the client to generate the MAC and to encrypt. These are two keys. There are two different keys that are used by the server for the same process in this case. So once a packet is sent by the client, the server can actually be sure that it is a confidential message, and can be sure that it is also verified for integrity in this case. So when you see a web page that is using HTTPS, you would know that these two services are guaranteed. And because TCP is an end-to-end protocol, that means that regardless of where your packet ends up going, regardless of what kind of routers or networks the packet jumps over, it is going to be guaranteed for confidentiality and integrity in this case. Okay. After that, we will discuss the handshake protocol. Basically, how do two devices, the client and the server, that have not necessarily talked to each other before, be able to, first of all, identify each other's capabilities and choose which a cryptography algorithm or algorithms will be used between them, and also agree on the key. And so you will see that the handshake protocol is the one that does that. And the handshake protocol takes place after a TCP connection has been established. So you have the TCP connection request and response, and then you can actually start the handshake protocol, which has basically 4 phases. It starts with establishing security capabilities. Basically, both sides tell each other what kind of capabilities they have, what kind of cryptography algorithms they can support. And then the server starts by providing its certificate, if it's available, and basically how to establish its key, how to exchange its key. And then the client also may send its certificate and provide key exchange, and then the system is finalized, or the handshake is finalized. You will have to note that exchanging certificates is optional in SSL. The only thing that is mandatory is the operation of the record protocol, so confidentiality and integrity. Authenticating both sides is actually optional. You can have one side, which is the server authentication, or you can have both sides, which is the server and client authentication. So depending on what you have, some parts of the handshake protocol may not actually be there. And let's now take a look at the details. The details, basically the client starts by sending what is called the client hello message. And the client hello message contains the version of the protocol, the version of the TLS protocol, the session ID, which is an ID for this security association, the cipher suite. The cipher suite is basically the set of cryptography algorithms that the client supports, okay? And the client will send these algorithms in the order of decreasing preference. So it will insert the algorithm that it prefers the most at the top, and will actually send all the other algorithms after that in decreasing order of preference, and will also include initial random numbers to prevent replay attacks, and will include compression methods if they are available. So basically, the client will send all the capabilities that it has, whether it has a compression method or not, all the cryptography algorithms, and a nonce to prevent replay attacks in this case. The server will respond with the server hello. It includes similar information, but in the cipher suite, instead of actually the server sending all the algorithms that it supports, it will send only one that is common between itself and the client. So it will look at the list that the client has sent, and it will pick the highest one that it can also support, that the server also supports, and just sends that back to the client saying, okay, you support that, and this is on the top of your list. I also support that, and let's just use it. So in the server hello that is sent after it's received at the client and the server will both now know what kind of cryptography algorithms they will both use. Now, it's not just encryption that they agree upon. They also agree on how they will exchange a key, because SSL and TLS support several ways of establishing a key. For example, they support using RSA. One side generates a key and encrypts it using RSA and sends it to the other side. They support Diffie-Hellman in several forms. They support, for example, the anonymous Diffie-Hellman, which is basically no authentication whatsoever, and we know that this is vulnerable to man-in-the-middle attack, but it is supported by TLS. It also supports authenticated Diffie-Hellman, and supports authenticated Diffie-Hellman based on several methods. For example, based on the certificate alone, or based on an additional digital signature based on a public key that is generated and sent from the server to the client, or from the client to the server. So there are different ways of agreeing on the cryptography parameters and on the key exchange mechanisms, and everything will be established in the first phase of the handshake protocol. After that comes phase 2, which is the server side. The server sends a certificate, sends key exchange information, and may also send additional messages for the client to reply back. For example, if the server also requires that the client authenticates itself, then it will send a certificate request asking for the request of the client. If it doesn't require that the client authenticate itself, then it will not actually send a certificate request. In the message that is labeled a server key exchange, the server will send all the information necessary for the client to calculate the key that the server will use to encrypt and to provide integrity. Okay, so if it's Diffie-Hellman, for example, it will send the prime number, the exponent, the prime root, and it will send also the public key. Okay, so all the information, if it's RSA, then it will send the modulus and it will send the public key as well. All the information that the client needs to calculate the key will actually be included in the server key exchange message. Once the server is done, it will send a message saying server hello done, meaning I have no more messages to send to the client. Now the client has its turn in step 3 or in phase 3. If a certificate request was sent by the server, then a certificate will be sent by the client. If the client doesn't have a certificate, then the client may actually send a message using the alert protocol that we had discussed before, and we will discuss it again in a little bit, saying I have no certificate in this case. And the server has the right now to take a certain action, either, for example, refuse a connection or accept it, but with certain reduced features or something like that. Same thing for the certificate that was sent by the server in phase 2. If the client does not recognize the certificate or cannot authenticate the certificate properly, then the client can actually terminate the connection in this case. Okay. In phase 3, after the client sends the optional certificate, if it is there, the client will also send all the information necessary for the server to establish the key that the client will use in, or the keys that the client will use in the record protocol. Okay, and if the server certificate was verified correctly, the client will also send a message saying the certificate is verified. After everything is done, then there is another protocol that operates in step 4, which is the change CipherSpec protocol, that basically changes the status of the connection from negotiation to finalized, and now the client and the server can exchange application layer messages. So you will see that the handshake protocol may take 3 or 4 additional round trip times to establish a secure association or security association between the client and the server. This is an additional to the round trip time that is needed to establish the TCP connection. So definitely SSL and TLS will add a little bit delay to your connection in this case. Okay. We discussed the change CipherSpec protocol. The alert protocol is responsible for conveying alert-related messages between peers. Okay, and the alerts are of 2 categories: either a warning or a fatal alert. A fatal alert meaning that the connection has to be terminated at once. Okay, it's either an expected message, a bad MAC, a decompression failure, the handshake wasn't successful because, for example, they didn't agree on a cryptography protocol or the certificate wasn't authenticated. Okay, these are, sorry, the certificate is not authenticated. That's actually a warning. Okay. The fatal messages will lead to the security association being revoked and the TCP connection being terminated as well. The warning will leave it up to the client or the server to determine what to do. This actually includes no certificate or bad certificate. If you think that the client, this is actually what you get when you click on a link and you get a warning message saying that this website looks fishy. And then it's up to you. Either you continue or you return back to your previous page. Okay. This is what happens when your client, when your browser doesn't recognize a certificate or expects a certificate but doesn't get one in this case. And this is the responsibility of the alert protocol. Now, if you are using HTTPS, then that means that you're using SSL or more likely TLS at the transport layer. The port number would be 443 instead of 80. And what actually gets encrypted in the message is basically all the content of the HTTP message itself, including the header, including cookies, including the content of the forms that you send, the URL, the contents of the object itself that you that is sent back to you from the server. Everything is actually encrypted in this case. So if HTTPS is used, no one can actually look at the content of the HTTP requests and responses that you send and receive. Now, does this mean that no one can actually know what you're doing? Well, they cannot recognize the content, but using the IP addresses, they can recognize what you are sending and where you are sending, where your packets are going, and where they are coming from. And this is where IP security comes to play a little bit of a role in improving the security features of the internet itself. Now, in SSL and TLS, we have seen how security is provided at the transport layer. Now we want to see how security is provided at the IP layer. Okay, and the IP security protocol relies on three main protocols. Okay, that implement the security features. These are the authentication header protocol, the encapsulating security protocol, and something called the key management and session setup protocol. And all of that needs the IP security architecture, which is another RFC, to basically coordinate how all these protocols work. Okay. Um, for IP security to execute its features, it needs an additional header. Just like TLS and SSL required an additional handshake and additional information is included in the message, IP security also relies on an additional header that is inserted between the IP header and the payload to perform the security features in this case. Now, when IP security was being designed, there was an obvious challenge that they had to meet. When you want to include security at the transport layer, it is relatively straightforward because you rely on the client and the server already having a connection between each other. They already have to negotiate parameters with each other in TCP. So if you build SSL on TLS on a connection-oriented protocol like TCP, you have already the, let's say, the infrastructure to build your security association, to exchange parameters, to exchange keys. All of this is readily available for you to build on. There is no such mechanism at the IP layer because everything at the IP layer is connectionless. When you send a packet, the routers actually treat each packet independently. And so there is no mechanism for you to build a connection or a security association between devices. And now this becomes a challenge. Who is going to add the IP security header? Who is going to read it? Who is going to remove it? Okay. These are all challenges that are addressed in IP security. For example, in the figure that you see here, you see that the client is the one that adds the IP security header, and there is a gateway somewhere that reads it and remove it. And so the end client in this case doesn't get the IP security header, maybe because it doesn't support IP security. This can be one of the scenarios. Another scenario can be that the IP security is sent all the way from the client to the final destination. It is the one that reads it. IP security as a system provides a lot of flexibility and a lot of options for people to use and people to choose from. Okay. What does IP security support? Now, just like SSL and TLS, it supports authentication and confidentiality. It supports them in the two protocols that are available. There is a protocol called authentication header and a protocol called encrypted security payload. The authentication header only provides integrity and authenticity. The encrypted security payload, or ESP, provides mainly confidentiality, but you can include authentication and integrity as an option, but it is mainly for confidentiality in this case. Now, how do we solve the problem that IP is a connectionless protocol? Well, basically, you don't want devices to build a connection between them because then you will actually be terminating the connectionless property at the IP layer. Instead, you have a security association. Now, a security association is between two devices. However, a security association is one way, meaning that a security association is one device being able to tell another device that this is basically the parameters that I will use either for the ESP protocol or the AH protocol. So the key management protocol that is part of IP security provides ways to establish a security association. Now, if you want the security to be mutual, if you want two devices to be able to secure their data, then there has to be two security associations, one in each direction. There can actually be more than one security association between two devices. So if you have A and B, you can have one security association in this direction or more. and you can have one security association in the opposite direction or more. Why do we need that? Because each security association will only use one of the two protocols, either AH or ESP. That means that a security association either is going to support only integrity and authenticity, or is going to support only confidentiality with an additional option of integrity and authenticity in this case. If you want to have both, then you may actually want to have more than one security association, and we will discuss this issue in a little bit throughout the lecture. Okay, how does IP security now support its services between two devices? There are mainly two modes. They are called the transport mode and the tunnel mode. The transport mode is the only one that can be used in end-to-end communication, or the main one that is used in end-to-end communication. Typically, the transport mode will provide protection only to the payload, meaning that you provide authentication. If this is your message, this is your payload, and this is the IP header, and the payload obviously includes the transport header as well. The transport mode will provide security services to the payload only. And typically, the security services that are provided in transport mode are authentication and integrity. On the other hand, in the tunnel mode, what you do is you take the entire original packet, including the IP header, and you encapsulate it in an additional IP header, and then you can provide security services to the entire original packet. Okay? That means that you can encrypt the entire packet, you can provide authentication and integrity to the entire packet. However, you do that only between the endpoints of the tunnel. If the endpoints of the tunnel are the original sender and the final receiver, then you have your properties ensured for the entire journey. However, this is unlikely to happen, because if you do the tunnel mode between the original sender and the receiver, then that means you're actually adding an additional IP header that will include the same information that was in your original IP header, which is pointless. Typically, then what you would do is that you have a tunnel mode between gateways. Okay, so you have a tunnel established between gateways, and you have here the original IP header is in the clear. Okay, and here you have the original IP header is in the clear, meaning that the tunnel mode will provide anonymity, but only between the endpoints of the tunnel. This is because the additional IP header that is inserted at the entry point of the tunnel will include the source IP address of the entry point and the destination IP address of the exit point. And everything in the tunnel, everything in the packet, the payload of the packet, including the original IP header, will be encrypted. So no one will be able to read where the packet is going inside the tunnel. Once the packet exits the tunnel, then the original IP packet will be in the clear. And so in this case, people will be able to read it. So the anonymity of the user is now vulnerable at the first network and at the last network, but not in the tunnel. And these two figures basically illustrate. The transport mode, you can actually provide security services between end to end or end to end. And here mainly we are talking about authentication. The tunnel mode basically acts as a VPN. You provide security services between the endpoints of the tunnel. You add an additional IP header that includes the source IP address of R1, which is the entry gateway, and the destination IP address of R2, which is the exit gateway. And nothing in the packet can be read between R1 and R2, but before R1 and after R2, the original IP header will still be in the clear. You'll have to notice that in transport mode, there is no anonymity in this case. You can only provide authentication, and you can also encrypt the payload itself, but the IP header itself has to be in the clear because the routers have to read it in order to do routing. Okay. Now, a key feature or a key part of the IP security protocol is what are called security policy and security association. We have already talked about a security association briefly, which is basically just the one-way relationship between a sender and a receiver. And the security association is identified by three parameters. The IP address of the destination is the key parameter in this case. You are actually saying this is a one-way relationship between me and this device. Then you have a security protocol identifier. It basically identifies the version of IP security protocol. and the security parameters index is an identifier of this security association. Okay. As we said, a security association will support either authentication header or ESP, but not both. After the security association, you will have a security policy database. And it is similar to the one that you see on the table on the right. Basically, this security policy database, or SPD, tells you how to handle each packet. For example, if you see the entry in the first row here, this entry is basically saying if the upper layer protocol is UDP, and if the local IP address, which is the source IP address, is this one, and the port number is 500, it doesn't actually matter what the remote IP address is, you can bypass this packet, meaning that the packet does not have any security or IP security features. IP security can just bypass it and send it as it is, meaning that this particular application, okay, is unprotected. I don't care actually about protecting it. And the comment here is that this is related to IKE. It is actually the packet that is used to establish keys between two endpoints of an IP security association. So obviously they cannot be encrypted because there is no key that has been exchanged before, and so they are bypassed. Also, if the protocol is ICMP, you can bypass. These are mainly error messages. You don't need to protect them, so just bypass them as they are. Now you will see for the remaining ones, the local IP address is all the same, meaning that this is actually the source IP address. There is an option in the security policy database that you can actually aggregate. You can actually say this is a network. So for these networks, for these collection of IP addresses, do this or that. This is typically done at gateways. If you're implementing IP security at a gateway, you may actually want to provide a security service for the entire network and not just for a single IP address. Here, for example, if the remote IP address is this network, 1.2.3.0/24, use ESP. This means that there is a security association with a gateway in this network that uses ESP. On the other hand, or similarly, if you're contacting 1.2.4.10, also use ESP. Okay. There is another entry here saying that if the destination IP address is 1.2.4.0, discard, meaning that you should actually throw away this message. This is what is called a demilitarized zone. This is what, if you're sending to this address, it will be dropped. There should be an entry in the secure policy that tells you what should happen if a packet is not part of any of that. If a packet is sent somewhere over the internet, for example, where there are no security associations, what do you want to do? Do you want to bypass? Do you want to drop? What exactly do you want to do in this case? If there is no such entry, such as this last entry, anything where a security association is not already defined will be dropped. And this is actually becomes clear in these two flowcharts. If you look at the flowchart of the outbound packet, now there is a packet coming from the transport layer. First thing that you will do is that you will search the security policy database. If no match is found, the packet will be discarded. Okay, this is why it is necessary to insert a match, and a match can actually be something like this last row here. If nothing else matches, so basically in looking at the security policy database, you will look at the largest number of matches. If there is nothing that matches except the source IP address, then this is the match that will be used. If there is no match whatsoever, then the packet will be thrown away. If there is a match, then according to the match, you will determine the policy. If the policy is discard, then you will discard the packet. If the policy is bypassed, then you will just forward the packet as it is. If the policy is protect, then you're going to look at the security association database to know exactly what you should do. Is the security association with the destination done according to the authentication header or the ESP header? If it is one of them, then you're going to actually use the one that is already defined. If there is no match in the security association, that means that you have to establish one in this case. That means you go to the key exchange protocol to establish the security association, and accordingly, you either use the authentication header or the ESP header in this case. These are for the outbound packets, the packets that you send. For the inbound packets, once you receive a packet, if it is a normal IP packet, meaning that it is not protected by IP security, you will search the security policy database to see what should be done with it. If there is an entry, then according to this entry, you will basically figure out if the entry is bypassed, then you deliver to the upper layer. If not bypassed, then you have to discard the packet. Meaning that if you don't manually or intentionally insert an entry that says bypass the packet, then you will have to discard the packet. Now, if the packet is IP security, then you will have to search the security policy database and see whether there is a match. Again, if there is no match, you will discard the packet. If there is a match, then you will process the packet according to either the authentication header or ESP, and then send it to the upper layer in this case. Okay. Now we take a look at what the authentication header looks like. This is basically the header that gets added between the IP header, the original IP header, and the payload of the packet. It includes the identity of the security association to which this packet belongs. The sequence number basically prevents replay attacks, and then the authentication data. The authentication data, there are several protocols that are actually supported by IP security. The one that is mostly used is actually HMAC in this case. And the key that will be used has to be exchanged beforehand by the key exchange protocol. That means the security association must have been established beforehand in this case. The ESP protocol, we said that it provides confidentiality mainly, but it also has option to provide authentication and integrity as well. If there is authentication and integrity, then this part of the header will be added also. Otherwise, then you still have the security parameters index to provide to identify the security association and the sequence number to prevent replay attacks. And then it depends on whether you are actually in the transport mode or tunnel mode, what will be actually encrypted. If you are in transport mode, then encryption is going to apply to the payload only. That means you will encrypt from the TCP header and to the data and the ESP trailer as well. If you are in tunnel mode, then what you will see here is that you take the original IP header and you encapsulate it in a new IP header, and then everything that is beyond or starting the original IP header will be encrypted in this case. This is what the difference is between the transport mode and the tunnel mode. Okay. On the other hand, if there is authentication, whether it is the authentication header protocol or the ASP protocol, the authentication applies to the ESP header if it is there, and the payload as well. That means what you will hash actually everything in the TCP header, in the data, in the ESP trailer. And if you add an ESP header, which basically includes the security parameters index and the sequence number, they will be hashed as well. And this is the same in transport mode and tunnel mode. Now you will notice here that the original IP header and the new IP header are not included in the authentication. This is not 100% accurate. Actually, parts of these headers will be included in the authentication. The problem is that you cannot actually include everything in the IP header in the authentication because there are fields that get changed from source to destination. For example, there is a field called time to live that is decremented by 1 in every hop. You cannot include it in the authentication in the first hop or in the original source because the other hops, the other routers along the path will change it. So you cannot authenticate it initially. Otherwise, every device between the sender and the receiver will have to recompute the hash. And this is not the case. What you include in the authentication in the original IP header, or in the IP header in general, are what are called immutable fields, the fields that don't get changed between sender and the receiver. The examples include, for example, the source and destination IP address. And it is very important to include those in the authentication part so that the receiver would know that where this packet is coming from. If someone actually sends a packet from a fake IP address, you will now be able to actually to catch it because you are including the hash of the IP addresses in the authentication data itself. Okay. Now we discuss what can actually be established in terms of security associations between sender and the receiver. If you are actually talking about end-to-end, then there can be more than one security association between sender and the receiver, depending on what kind of security services you want to provide. If you want to use the authentication header and you want to use ESP as well, then you can have two security associations. If you are actually having different types of packets between sender and the receiver, and each type of packet is required to be treated differently, then you can have more than one security associations, either one within the other or parallel to each other in this case. You can have several security associations between the endpoints, and then you have a tunnel between two gateways. So in this case, there will be security features or security services that are provided between the endpoints of the tunnel and other security features that are provided end-to-end. Okay, or you can have a tunnel just between the gateways, and then before and after the gateway, it's just regular IP. You can also have a tunnel between the host and the gateway itself. Okay, there are several things that you can do or you're allowed to do in IP security. It just depends on what kind of services that you want and where do you want to implement. Okay. Now this finalizes our discussion of the internet security. What we will do now is that we will take a look at the implementation or the high-level overview of the end-to-end encryption system of WhatsApp. Um, you probably remember that end-to-end encryption was not there in WhatsApp from the beginning. So basically, before end-to-end encryption, there was link encryption, meaning that the data in WhatsApp was encrypted between your phone and the WhatsApp server, because WhatsApp is obviously client server. And then the server would decrypt, get the message, encrypt it again, and then send it to the destination. So anyone outside of these three parties will not actually be able to read the message. But the problem was your privacy was vulnerable at the WhatsApp servers themselves, because they have to, in this case, they have to decrypt the message in order to be able to forward it to the destination. Then your privacy is not assured at the WhatsApp servers themselves. And so because they wanted to address that, then they proposed end-to-end encryption, meaning that you still send the message to the server, but the server doesn't decrypt. There is now a security association that is going to be negotiated between the endpoints, between your phone and the destination phone. The server just needs to know where the message is going to be sent. It basically just needs to know who you're talking to, but does not actually read the content in this case. The details of the protocol are called actually the Signal protocol, proposed by a company called OpenWhisper Systems. Okay, and one of the main features that it wanted to support is that even if a user's key is physically compromised, the attacker cannot decrypt previously encrypted messages. This is what is called forward secrecy, meaning that all the messages that you have sent before are actually protected. How does the protocol work? First of all, upon registration, when you download WhatsApp and you create an account, you generate three types of public keys. There is what is called the long-term identity key. This is generated once and it doesn't actually change, doesn't get rotated. So it is a one-time long-term identity key. There is also a medium-term key. This is also generated at installation, but it is rotated periodically, meaning that you take one bit and you rotate it, for example, clockwise. I don't know the rotation mechanism specifically, but this is basically what happens. Now, all the keys are generated locally at a client. The server doesn't generate them for you, otherwise this will negate the purpose. You generate the keys as pairs. So when I say you generate a long-term identity key, this is actually a pair of public and private long-term identity keys. You send the public one to the WhatsApp server, but you keep the private one yourself. The medium-term key is also a pair of public and private. You send the public one to the server, but you keep the private to yourself. And if the medium-term key is rotated, then the private key that is associated with it will be different as well. Now, when the client sends the medium-term key to the server, it actually digitally signs it using the private key of the long-term identity key in this case. So now the medium-term key is digitally signed by the long-term identity key. The client also generates a set of one-time keys, and they are actually sent to the server. All of them digitally signed as well. Now, these are the ones these are the keys that are used to establish a session. Once you want to send a message, you will use actually symmetric encryption. So these three long-term, medium-term, and one-time keys, the public keys, will be used to negotiate, will be used to actually calculate what is called a master secret. So basically, what happens when you want to talk to someone, you go to the server and you ask the server for their three keys. You ask for the long-term identity key, the medium-term key, and one of the one-time keys that have been sent by that other client to the server. You get these three keys and you will use them in addition to your private keys, according to a system that is very similar to Diffie-Hellman, to generate something called a master secret. Once you generate the master secret, you will feed the master secret to something called the key derivation function. Okay? The key derivation function is nothing but a constant algorithm. You feed to it a master secret and out comes the root key. And the root key is 32 bytes. You will feed the root key to another key derivation function to generate a chain key. And you will feed the chain key to another key derivation function to generate the message key. And the message key is 80 bytes. Out of those 80 bytes, 32 are used for confidentiality using AES 256, and another 32 are used for HMAC using the SHA algorithm, also 256, and the remaining 16 bytes are the initial value. Okay, so again, when you want to send a message to someone, you go to the WhatsApp server, you ask for their long-term identity key, their medium-term key, and one of the one-time keys that they have sent. You take these, you use them to generate a master secret. You feed the master secret to a key derivation function to generate the root key. You feed the root key to a key derivation function to generate the chain key. You feed that to a key generation function to generate the message key. And the message key is the one that you use to encrypt the message and to generate the HMAC of the message. Okay. Once you do that, you can then send a message to the WhatsApp server. Now notice here that the recipient doesn't have to be online at all. This is actually the point of having a non-real-time chatting system. You can send someone a message while their phone is turned off. In this case, the message will actually stay at the WhatsApp server. It will not actually be forwarded to the client. Now, once the client becomes online, they will contact the WhatsApp server and ask for all the messages that have been delivered to the client. If the client receives the message from someone that they have no security association with, then the recipient will ask the WhatsApp server for the same information of the sender, the long-term identity, the medium-term key, and one of the one-time keys, and it will feed that into an algorithm to generate the exact same master secret that the sender had generated. And using the same key derivation functions, the recipient will be able to generate the root key, the chain key, and the message key in this case. And then using the message key, once they have the message key, they can retrieve the message from the server and decrypt it and check its integrity to know that the message is actually doesn't have errors and has not been manipulated in this case. Now, every time you want to send a message, you will generate a new message key from the chain key. Every time. That means every message you send will be encrypted with a new key. Every time you send a message, it is encrypted with a new key. This is a very high level of security. It's a very sophisticated system, and it ensures that even if old keys are compromised, you cannot actually decrypt future ones because the future ones are actually generated with a different key in this case. Okay, this is, let's say, a high level overview. Final thing I will what I forgot actually to mention is that every time the chain key is used to generate a message key, the chain key is also rotated. So the key that is used to generate the message key is also rotated every time as well. The final thing I will mention about this protocol is actually the special features. What happens when you want to send media, when you want to send a picture, for example, you send the picture or the video or whatever, you send it encrypted, and it is saved in a cloud store, and then the server sends an encrypted pointer the sender generates an encrypted pointer and send it to the destination so that it can actually download and receive the media in this case. If you have a group chat, then there is actually a pairwise association between every two members of the group. because when you send actually a message, you are sending it encrypted or copied n times each time according to the security association with every member of that group, and then the WhatsApp server simply just distributes them. Okay, voice is encrypted with RTP, so you still actually have it end to end, meaning that the WhatsApp server in the middle doesn't actually learn the content in any way. Now, this has been true up to I think 2017 or 2018, when WhatsApp started to lift some of these restrictions so that they are able to learn content. It happened actually after the Cambridge Analytica scandal. Basically, they wanted to prevent the spread of malicious information. And now there are actually flags that are inserted in the messages so that WhatsApp is able to learn if content is being spread many times. So, for example, if you send a message once, it is flagged. If you send it 100 times, then WhatsApp will be able to detect that this is a message that is being distributed. And then they actually have ways to limit actually the spread of messages in this case. Okay, that's it. I hope you have enjoyed this lecture. I hope you have enjoyed the course, and we'll talk to you hopefully at some point.